They're actually they're a little harder than I originally intended them to be, and some of them are quite tricky. And I did put up some solutions. I want to bring your attention to one in particular, number 6. Number 6 was the integral from 0 to infinity (1 over x times log of x squared). Now, did anyone do this problem? Did anyone get an answer? It's as I said, it's quite a bit trickier than I had really intended. This is improper in multiple ways. To begin with, as the function approaches 0, clearly there's something weird happens here. We don't really know what that is, right? X is going to 0, but log of x is going to negative infinity. So that's a minor. It turns out it's totally unimportant. In this problem, it's totally unimportant. My dot cam is not working, but if you were to graph this, you'll see that, in fact, the function kind of goes like this. And so that's not really a problem as far as finding this integral. But you might notice there's something going on over here, and a little observation, you'd notice that whenever the log of x goes to 1, what happens to the log of x? X goes to 1. It goes to 0. So we have an asymptote here. And so we really need to break this up into 2 pieces. We have to look at from 0 to 1 and from 0 to infinity. Something happens out here in infinity. And I can't avoid giving away too much, but in order to do this properly, you would have to break it up into really 4 different limits, right? You first want to see what happens as you get close to here, and you'll find out that it all works out fine. And in fact, if you look out to infinity, it will also work out fine. But from somewhere over here to this asymptote, there's a problem, and it kind of negates everything else, because clearly if the area is divergent going this way, it doesn't really matter what happens on either side. So I want to highly suggest you take a close look at that and the other problems. Please note on number 5, I mentioned this in class, I had to change the limits because it makes no sense to find the square root of 1 minus 2 squared, the square root of 1 minus 2 squared that's undefined. So I changed the limit to 1, and then the problem makes some sense. So. All right, are there any, now that everybody, well, not everybody is still here, now there are more people here, are there any questions on this or on the homework that is going to be due Tuesday? Okay, it's very quiet. All right. Okay, again, please take a look at the solutions online if you haven't already. I think it take a look at the solutions after you've tried the problems. Okay. Today, we're going to reach a somewhat new topic. We'll fit into what we've been doing. The topic is differential equations. And explain what a differential equation is. This is a very, very big topic, and we're only going to do a brief introduction. We're going to look at it today, and we're going to look at it on Tuesday. Look at differential equations on Tuesday. Very important subject. Any of you who are interested in physics, biology, I guess probably any of the sciences. Also, these come up in economics and other fields. And you could take a course here just on differential equations, or you could go and get a PhD and study the field for many years. It's a very big field, but we're gonna do some of the basics today. First, what is a differential equation? A differential equation is an equation which includes an unknown function and its derivatives. Some of its derivatives. So a very simple example would be if I have some function f of x. I said f of x is equal to some constant times the derivative of f of x. This is a very simple differential equation. As a shorthand, we might write it this way. We might say y equals c of y prime, where it's going to be understood that y is not just a variable in the normal sense. Y is a function, and in this case, you can think of it as y of x. Right? We might also write this as y equals c y dx. And later in the day, you'll see there's some advantage to using this notation. All right. Like an integral, the solution to a differential equation, you often get a family of solutions. You don't just get one solution, but with some initial conditions, you can sometimes narrow it down to a particular solution. So, as a first example, we're going to look at the growth of a population. This is a very common problem that comes up, and you've probably seen the solution already, but you probably haven't seen it in this context. So this could be a population of bacteria, animals in an environment, or even people. And we make the simplifying assumption that the population increase is proportional to the population itself. So we would write that this way. Change in population over time is some constant. We're going to use k times the population itself. Again, think of p as a function of t. It's not a variable, it's a function itself. Okay. I guess I'd really like to write this time. I'm going to write this as derivative of p of t equals k p of t. And I'm going to divide both sides by p of t. And then to solve this, I'm going to find the integral of both sides. So, like so. This is with respect to t. So on the left, we get a very familiar pattern, and we get the log of the absolute value of p. And on the right, we're going to get kt plus some unknown constant. Now we can do some simplification immediately. We know that populations are always positive, so we don't really need the absolute value signs. And we can solve for p of t by raising both sides, raising e to both sides. And we're going to incorporate this constant, which is added to the exponent as just another constant that we're going to multiply by e to the kt. So we end up with p of t a e to the kt. Okay, so we have a differential equation, fairly simple one to solve, and we have a family of solutions here. Specifically, this constant a provides a family of solutions. K is something we presumably we have as the rate of growth with respect to the population. Okay, so I'm going to move this over here. So now, what I want you to think about is what if we have some initial conditions? So say, for example, we know that at p of 0 times 0, we have a value p of 0. And at some later time, we'll just say p of 1, we have p of 1. So we can take our equation and we can plug in. So at p of 0, we have a e to the 0, or 1, a, which is our p of 0. So we now know that our function p of t is p, the initial population, e of kt, and if we now plug in p of 1 here, we'll see that p of 1 equals p0 e to the k. Which is equal to p1. So if I solve for k now, I get e of k is p1 over p naught, or k is just the natural log of p1 over p0. So given these initial conditions, I now know that my solution is p0 e to the log of p1 over p0 times k, times x, times t. Okay. You might note that in this particular solution, the function e to the x plays a very important role. And as we will see later on, not today, it performs a very important function in solving more complex differential equations. Okay. Now, we didn't really actually give values here. We just picked a number. But it might be useful to think about what this actually looks like. If we were to graph this function, So all of these solutions will go through P0. But depending upon the value of k, this exponential function could actually be could rise very slowly, or it could rise very quickly. And this is very typical for a differential equation. That you will, again, you'll see some kind of pattern here, but again, it's the initial conditions that will allow you to tone it down. Okay. By the way, this is a very simplistic equation for this particular model. If you think about a population growing, this works if the population has unlimited resources. It can grow without limit. But all populations, especially humans, have some limitations. So at some point, this equation itself will break down. We could enhance this. We can enhance this this equation, the original differential equation, and we could add some term here. We could say at some point the rate of change has to decrease by some unknown factor here based on running out of resources. We may have time to look at that problem a little more closely on Thursday. Okay. So that's one very classic example. It's probably the simplest example. I'm going to show you one more example from physics that, again, it's a very basic problem, but it's actually quite a bit more complex. So let's see. Anybody here who's a physics major? Anyone here taking physics? Okay, a few. All right. Well, we'll do this slowly. So I don't want to lose you on the physics. I want to lose you on the math. Okay. So in physics, we have a principle called Hooke's law, and it applies to some different scenarios, but the one we're going to look at here is we have a spring and some kind of mass attached to it, and this is on some kind of frictionless surface. It's attached on one end, and this mass, what happens if you pull a spring, it's going to go back and forth. So the physics principle we have to start with, Hooke's law says that under certain conditions, a spring like this will obey the equation force equals some constant times the displacement, but in the opposite direction of the displacement. So if I take this spring and I pull it this way, there's a force going this way, and if I push it this way, there's a force going this way. Okay, again, some basic physics tells me that the force on an object will equal the mass times the acceleration if you release this, if there's no force keeping it in place. So we replace that and we get mass times acceleration equals minus kx. And we divide through by m, creating just a unified constant here, minus km. And then we have to go back to something I hope everyone's aware. Acceleration is, what's the definition of acceleration with respect to x? You didn't do any of these problems? Yes, Sam?
The second derivative.
It's the second derivative, exactly, with respect to time. So our differential equation then becomes d squared x t squared equals minus k m over x. Note x here, think of x again like the way we're thinking of y. X is a function of t, right? Okay, that's the physics. You don't have to really worry if you didn't understand the physics. You just have to get to this differential equation. Yes, sir?
Right, this is just something I've always wondered. Why is it d squared x over dt squared? Like, why is the 2 change between the top and the bottom there? I've just never understood that.
That's a good question. I'm going to think about that for a second. First, I'll give you the throwaway answer, which is the inventor of this notation decided that's how it would be. But of course, you might want to say, well, wait a minute. Like, there's got to be some rationale to it. I think what you should do is think of dt. I think you should think of dt as some very small delta t, which now we're squaring because we're dividing by it twice. Location divided by time is velocity, and then the change in velocity with time, you're dividing by that small number twice. The real question then is, why is it d squared x? And I think the answer is that d we're thinking of as an operator. In other words, it's not a variable here. It's saying we're operating on this x value, and we're doing the same operation twice, this integration operation. I don't have a better answer off the top of my head. Okay, but that's a good question. I mean, it's, we're going to, later today, we're going to see where, for arbitrary reasons, this notation is very useful to you as a student. But it's just notation, right? Again, everybody understands this is not a fraction, although it looks like a fraction. Okay, we're going to take a different tact in trying to solve this. Instead of attempting to integrate, I'm just going to ask this question. We're looking for a function, and if you differentiate that function twice, you get back the function times a constant, but in the opposite direction. Now, what kinds of functions do we know of that have that property? This may not be the way you parse the world in terms of thinking about calculus, but it's a good time to think about that. What kind of, so let me ask a different question, a simpler question. If I said, I have a function, I differentiate it, and I just get a constant times that function, what would you think of? I know it's late, but I know we're not asleep yet. If I wrote this, e dx f of x equals f of x, what would you think of? E to the x, all right. So we can do that, right? Now I want you to think of a function where you find its derivative twice, and you end up with the same function, only with a negative sign in front of it. cosine and sine, right? So we're going to, somewhat arbitrarily, we're going to create what we hope will be the solution to this, a function, and we're going to give it some arbitrary constants. I'm going to give it a sine of, and then we're going to use some constant, arbitrary constant t, plus b times cosine of rt, plus, you know, this is displacement, so this will take care of, well, where did we start? Where did we start this?
What does R represent?
Sorry?
What is R?
It's just an arbitrary constant. Why am I using r? I don't have a good answer. It's the constant I want to use today. Well, this may help you out. If you're a physics major, I might want to use omega, right? But I'm not. I'm going to use r. Okay, so let's take a look at this. Let's find its derivative. Derivative of x with respect to t. Okay, derivative of the sine is the cosine. Using the chain rule, we're going to have to multiply by r. So we get ra cosine rt. Derivative of the cosine is the negative sine. So we're going to end up with negative rb sine of rt. And our constant goes away. And now we're going to repeat that because we're looking for the second derivative. So the second derivative, again, we go through the same process. Now we get negative r squared a cosine rt minus r squared b cosine f. I changed the sign here. Cosine rt. And let me rewrite this as negative r squared a sine of rt plus b cosine of rt. Okay, well that's good because a sine rt plus b cosine rt looks just like our original function, except for the c. And we want that to equal, the second derivative to equal minus km times the original function. So how do I get that to work? If I set negative km equal negative r squared, I'm going to get that r is the square root of k over m. So that would give me at least some place to start with here. A function x of t equals a sine square root of k over m t plus the cosine square root of k over m t. Again, plus some arbitrary constant. Okay, that provides us with a really wide range of possible functions. Right? Recall this is a family of functions. The trivial solution shows up when a, b, and c are 0. This spring is just where it wants to be, and we let it go, and it doesn't move at all. That would be one set of starting conditions. Okay, let's think of something a little more creative. what if at time 0 we stretch this out? We're going to stretch it out an offset of x equals some value d. So that tells us at 0 it's going to equal d. But we're not going to give it, we're not going to push it. So the derivative, the velocity at 0 is going to be just plain 0. To understand what the acceleration is at that point, we have to go back to our physics here and say, all right, the force at this point is minus k over x. So the acceleration is minus k over m times x, which is d, right? So the acceleration will be minus k m times d. Okay, these are our initial conditions, and we want to try and use those to find some of these arbitrary constants. All right, so let's try that. Plugging 0 in here, right, x of 0, we get the sine of 0, so this goes away. Cosine of 0 is 1. Yes, right, times d, plus c, but we know that's our starting offset d. So let's keep this equation here. All right. What does this tell us? All right. Let's take a look at our velocity here. First derivative. We have r, which is square root of km times a, cosine, which is cosine of 0, which is 1, minus, again, square root of km b, sine of 0, which is 0, and that's equal to 0. Well, that's nice, because we can conclude immediately that now a equals 0. We can just, for this particular solution, we can just eliminate this term. And now finally we want to look at the acceleration. All right, let's plug the acceleration in here. So this was x prime. So the acceleration at 0 is now r squared, negative r squared, or negative k over m, times b, cosine of 0, which is 1. But we know that's equal to what? Minus kmd. So that tells us b equals d. If we plug b equals d in here, it says b plus c equals d. So now we also know that our arbitrary constant c is also 0. So finalizing this now, we have that x of t equals b, which is d, our initial offset, cosine of square root of k over mt. And this tells us the position of our object that's at the end of this spring within time, which is not a big surprise. It's a cosine function, right? It's going to oscillate back and forth. Okay. Any questions about this? This was a pretty involved problem, but we're gonna work up to things like this. Okay. I have a worksheet. Oh, wait a second. It's not ready yet for the worksheet. Okay. Before we do that, I want to make a point about differential equations. Differential equations, like some integral problems we have, can be very difficult to solve. But like integration, if you think you have a solution, it's much easier to verify that it's correct. In the case of integration, you just find the derivative, which is fairly straightforward. And in the case of differential equations, you can just plug in the equation, your function, and see if it works. Okay. Give me a second here. Okay, so as an example, I want to show you a specific differential equation, which is y prime equals y squared minus 1 over 2. And I want to suggest a possible solution, which is that y of x equals 1 plus a constant times e to the x over 1 minus that same constant times e to the x. Now, we have no idea how to solve this right now. So this is we're just going to see how easy it is to determine, is this actually a solution? Well, what are we going to need? We're going to need the derivative. So I'm going to use the product rule. I'm sorry, the quotient rule. So the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. Okay, we have to do a little work here. This becomes c e to the x minus c squared e to the 2x minus c e to the x plus c squared e to the 2x over 1 minus c e to the x squared. Okay, we can see this is going to drop here. And that's not right. have done something wrong here. Does anyone see my error yet?
It should be the plus, not the minus.
Where's the plus?
Middle of the,
Here?
yeah.
Okay. Thank you. Okay. So, again, this is just going to end up with 2c e to the x, all right, over 1 minus c e to the 2x, c e to the x squared. Okay, so that's my y prime. And I want to determine whether y squared minus 1 over 2 is the same as this. So I'm going to take this and square it. 1 plus c e to the x squared over 1 minus c e to the x squared minus 1 over 2. I think it would be over the space. I guess easy is the wrong word to describe this process for this example. I guess a better way to describe it would be within your capabilities. Okay, so on the left I'm going to have 1 plus c e to the x squared minus 1 minus c e to the x squared all over 2 1 minus c e to the x squared. And I want to expand these, of course. So 1 plus 2c e to the x plus c squared e to the 2x minus 1 minus 2c e to the 2x plus c e to the c squared
Not
2x. No 2x here. Is that what you were saying? Okay. All right, so what drops out? One's these, so I ended up with 4c e to the x over 2 times 1 minus c e to the x squared. Move this back to 2. Oh yes, it's just like what I want. So again, it's just algebra and a little calculus to determine that. Okay, any questions about this so far? Okay, now we're ready. There are 2 problems here I'd like you to try. So take a few minutes. So I just want you to do the first page, number 1 and 2. Okay, take a few minutes. made things too easy for you. I guess I didn't get the right one. I originally intended for number 1 to say dy dx equals kx. But as you can see, I've kind of solved it for you already, so you just need to figure out what c and k must be given the initial conditions, which is what I wanted you to do. So. So Liang's not here, right? Oh, okay. Then Yolanda? Okay. Everyone figured out what C is already? Okay, solution by inspection almost. Let's see, y dx equals c e dkt. So y has to equal what? Go like this. What happens? You get y over here, and what happens over here? What's the integral of c e to the kt? This should be, well, either this should be x and this should be x, or this should be t and this should be t. What's the function?
1 over k is kt.
Say again?
C and 1 over k is kt.
I apologize, I'm just not hearing you.
The C over k
C over k,
and E
to the k. Okay. So at 0, what do we get? C over K is equal to what?
50.
50. Okay. And at 10, we get CK equals e to the 10K. Which is equal to what? 25. So we can figure out K here, right? What's K? Well, 10K is log of 25, right? So K is log of 25 over 10. And if you plug that back in over here, you'll be able to find C. Okay. How about number 2? Is anyone having trouble with that? It should be fairly straightforward. We want to show that the second derivative of y minus 4y equals 0 is y equal to 1/4 e to the 2x minus e to the minus 2x. So the first derivative is y equals 1/2 e to the 2x plus e to the minus 2x. And then y double prime is now just e to the 2x minus e to the minus 2x. So if I take this, e to the 2x minus e to the minus 2x minus 4 times 1/4 e to the 2x minus e to the 2x, I of course get 0. So now we've verified that this is a solution, but we want to do one more thing. We want to show that y of 0 equals 0. We plug in 0 here, we get 1/4 times 1 minus 1, which is 0. And we want to show that y prime, the first derivative at 0, is 1. Well, now 1/2 times 1 plus 1, that's just 1. Okay, any questions so far? This will become clear. I know it's a little obtuse because this is the first time we're looking at this new subject. But when we come back from the break in a few minutes, we'll look at a particular strategy for solving some differential equations. So, we're going to take 5 minutes. So Richie's here, Dino's here. Is she Hal here? There you are. Hello. Ming is not here. Melanie?
What time did you get?
No, Melanie. Melanie's here. Cedric.
Second year.
Okay, question.
I think you should just take one. Just take one. She's a lot like this. Yeah, I tell
Well, okay, so first you have to find out. So y is equal to 50. You plug in 0, C10. Then plug in 10K over 10. Maybe I did something wrong. Nobody paid any attention. C over. Let's go over that when I don't think I did it right. Good question. I'll take it off. I mean, I just want to see if there are any quick questions I can answer. Yes?
Why do you take this one?
Well, what happened, you should know, because what you don't know is during the quiz, you should have taken half the class that you missed, the whole class. So there was a section on numerical integration which we never got to.
What was your time?
But you have a good excuse as to who foolishly did that homework. But everybody, almost everybody else turned it in anyway, even though we didn't go over the material. So you don't have to worry about it.
It wasn't over the 6 o'clock.
It's not really due today. I wanted people to come in with questions, but they didn't. So my subterfuge did not work. I can bring it in Thursday. I'd rather you bring it Thursday. Unless you don't, I'm not Thursday, Tuesday. Yeah, today's Thursday. I'd rather you bring it in. Okay. Now let's take care of you.
Why not?
Around. Your grade is not a secret.
Like 3 weeks later.
Do they want a number or a letter? They want a letter.
Because like, it's for like prerequisites. Like reading. No, for math, science,
Looks like an A. I mean, they're asking for it now, right?
Yeah.
Of course.
No, it's 7.
I assume, you know, I assume it's 5 credits.
Yeah.
He has to upgrade the final grade.
Excellent student.
Yes,
And today,
yeah, I know. Why?
You've gotten it already.
I know, I haven't. Yeah. Thank you.
I thought they there was some movie I saw this happened recently where the person they got in, but then they failed, they got rejected. They don't like that. Anyway.
Yeah, if you feel
Yeah, I did this wrong. I'll fix it. Yeah. I actually fixed it on the sheet. And then I thought I copied the sheet. I was curious. I thought I put it on my website, and then I downloaded it on my website. Let's see what it says on the website. Handout.
Yeah, I think it's like the same thing.
The right thing is here. And I just okay, yes.
What are you taking right now? It's like different. I don't think it'll transfer over as well.
Differential equations come a lot in physics.
I don't know.
Yes, I know. It's kind of strong. They also come up in biology. It's when you have a variable where what the variable is depends not just on external, time or whatever, but it depends on one of its derivatives. So the first example was how to do people, right? We have a million people, and they're reproducing at a rate of, say, 1 per 100. How much? 20. So in a year, the population is no longer a million. It's now a million plus, whatever, 5%, whatever it is. So we want a solution. We want to know what is the population over time. And that's a very simple one you've done before. You get an exponential function. But they're much more complex. Well, we did the one with the spring. That's a very simple one. In a star, right, you have gas, right, and you have pressure over a certain layer, but there's also gravity, right? So as you move inward, pressure has to get greater. The mass gets denser. Gravity gets because here the entire gravity of the sun, the star pulls in, all the mass outside doesn't. So you have a differential equation for state. It's very complicated, and you can't actually solve it the way we're solving it. It's like numerical. This is how 150 years ago, they thought that the energy of the sun gravitational collapse. The gas was collapsing energy is being light. But by doing this first calculation, they found that it's very similar. It was hot enough. Just on a theoretical basis, they found that reactions going on in the center. And they didn't realize this until, they didn't have an improvement of this until about 30, 40 years ago, when someone on the Earth in a cavern had a tank car of carbon tetrachloride, and he was measuring interactions with neutrinos. Because neutrinos, from the nuclear reactions, coming out of the star, they were directly used in measurement. Of course, at the time the measurement they found those, so they knew there were nuclear reactions going on, but the numbers were wrong, and they didn't know why. And then only about 10 years ago they found out that the neutrinos, which they thought were massless, actually have a mass. So they go through different states, and it explained the difference. I don't know if that helps anyone. You know, differential equations are very, very common. You haven't run into them before because you haven't taken this course yet. Okay, I guess, yes, questions? There's a plan for Tuesday. You make the mistake of reading it in. Now, the quiz is over here. We're over here. Okay? All right. I'm allowed to change my schedule a little since things don't always work out. Okay. So C must equal 0. Okay. Hello. Everybody back? Anybody? Would someone just take a look out the door and let anyone know? All right. So, first things first, I made a mistake on the worksheet, and I thought I could just ignore it, but you can't, because then you get a terrible situation. So what I really intended on the worksheet was dy dx equals kx. And if you use the same technique I used on the first problem, you would find that y equals some constant e to the kx. Let's verify that. dy dx equals k c e to the kx, which is equal to k times y. I guess I meant y here. Sorry. Okay. So that's what you were supposed to do if I had given you the right problem. And then the rest falls into place pretty easily, because if y of 0 equals 50, that's equal to c e to the 0, so c is 50. And if y1 equals 50 e to the kx, right? So that's just k. If that's equal to 25, then e to the k equals 1/2, or k equals the log of 1/2. So my apologies for a very confusing problem. All right. Before we get started, any other questions on what's going on here? Okay. Again, this is an introduction, so I'm trying to give you a little more information than you really need. And I want to talk a little bit about some terminology. This particular equation only has a first derivative. So this is called a first order, I should write that word clearly. This is a first order differential equation. Okay? We had another problem here. This equation has a second derivative. So this is a second order differential equation. Now, none of these equations that I've shown you so far is the variable or its derivatives multiplied by anything beyond a constant. So all the equations I've shown you so far are linear. With one n or two? Yeah. Linear differential equations. And again, I want to say, my own experience, my own background. I was a science student. I studied physics and astronomy. And I know that most, not all, but most differential equations you run into are at most second order. And most of them are linear, which is good because we're very good at solving those equations. That's not true of all equations. A notable exception is if you become an astrophysicist and you study general relativity. The general relativity equations are very notably not linear. That is, if you know a little bit about it, space is warped by energy, right? But with gravity, you get potential energy. So you have to include the potential energy. Anyway, that's what kind of nonlinear stuff looks like. Very complicated. We're not going anywhere near it today. Oh, we are actually going to look at some nonlinear differential equations, just not maybe by Einstein. Okay. So in particular, we're going to learn a technique for solving a certain kind of differential equation today. The kind of differential equation we're going to learn, there's a story that goes like this. A man comes up to his friend's house and he sees the man's on the porch. And the man wears glasses, but he doesn't have his glasses on. And he's feeling around on the porch. The man says, "What happens?" He says, "Well, I dropped my glasses somewhere. I'm looking for them." He says, "Oh, okay." So he gets down on his hands and he's looking around for them. And after a while, he begins to think that the glasses aren't here. He says, He says to his friend, I don't think they're here. And his friend says, oh, I know they're not here. I know I didn't drop them here. He says, well, why are we looking here? He says, because the light's better here. So, we're going to try and solve some differential equations. We're going to try and solve some that we can solve, right? Because the light is better here, Okay. So, what we're going to look at is differential equations of this form. They're going to be first order, but they're going to have the form derivative with respect to x is equal to some function of x times some function of y. That is, the x's and y's aren't mixed up, so you can't separate them. These are equations that have separable variables. Now, the way we go about this is we perform kind of a sleight of hand that the notation tells us we can do. What we do is we put the y's on one side and the x's on the other. So, in this case, we would say we want to put the y's over here, f of y dy. No, that's not right. 1 over f of y dy equals d of x, d of x, dx. Now, I say this is a sleight of hand because, again, these are not components of a fraction. These are not numerators or denominators. But the notation lets you do this. We then integrate both sides. And on this side we only have y. This side we only have x. When we're done integrating, hopefully we can now solve for y and have a solution. So let's do an example. Right? dy dx equals x squared over y squared. So I'm going to end up here with y squared dy equals x squared dx. I'm going to integrate. I'm going to get y cubed over 3 equals x cubed over 3. No, I did that wrong again. Nobody's watching me. Just yell out when I'm doing something so ridiculously wrong. Okay, integrating 1 over y squared, I get negative 1 over y equals x cubed over 3. So now I want to solve for y. So what's y equal to? Y is equal to negative 3 over x cubed. Right. I hope that worked. When I was integrating, I kind of ignored it, but you end up with constant integration, just like we always do when we're finding intervals. Let's check this. All right, let's see if this worked. All right. So the derivative of y is what? This is x to the minus 3, so we're going to end up with x to the minus 2. Divided by, well, it was divided by minus 3. Now it's divided by minus 2, right? The c goes away. All right, so we want to see what x squared over y squared is. well, x squared we know is x squared. Y squared is, well, y is negative 3.
You were doing the integration. You were actually doing the integration.
I didn't do the integration right?
No, for the negative 3 over x cubed.
What?
For the negative 3 over
Oh.
x cubed.
Yeah. A bad day, I know. Thank you.
No.
No. So look, x squared, this is y squared, right? Isn't that right?
1 over y squared. But I mean,
No, it was already x squared over y squared. Right? Yeah, this is. All right, let me do something really ridiculous. Let me look at my notes. Yeah. Okay, let's try again here. This is y cubed over 3. This is x cubed over 3 plus some constants. Right? So y must equal x cubed plus 3c with the cube root of it. Okay, that looks a little better. Okay, now let's see if that works out right. So y prime is, this is all this to the 1/3. So it's 1/3 x cubed plus 3c to the negative 2/3 times the derivative of this, which is 3x squared. So that's dy dx. And now we want to find out what x squared over y squared is. So x squared over x squared, x cubed plus 3c to the 2/3. Oh. Let's see, that cancels. So this is just x squared over x cubed plus 3c to the 2/3. My gosh, it works. They're the same. But there's more. See, I want to do a little bit more with this problem. What I want to do is give an initial condition that y0 equals 1. So if y0 equals 1, that equals what? The cube root of the square root, cube root of 3c,
3 plus.
or 3c equals 1, or c equals 1/3. So I have to add 1/3 here. Okay. Okay, let's just try one more. Well, actually, let me. Let's try one more. So this problem is y dx equals x squared y. Let me first ask the question: is it obvious that we can separate the variables? look. Is this obvious? Yeah, it's just that x squared, this is our function of x, and this is our function of y. Okay, so again, here we have 1 over y dy equals x squared dx. Integrate. We get the log of y equals x cubed over 3 plus a constant. And we raise this to the power, to the e power, right? So we have absolute value y equals e to the x cubed over 3 plus c, which again, you know, since this is in the x, since this constant of integration is in the exponent, it, you know, you can just take it out front as some other constant. And I guess we don't really care about the absolute value sign at this point. Right? So it's just y equals a e to the x cubed over 3. I guess we should test that again, shouldn't we? So the derivative of y with respect to x is a e to the x cubed over 3 times 3x squared. And that's supposed to equal x squared times y, which is a e to the x cubed over 3. Must have gone wrong somewhere. Oh, I'm sorry. There's a 1/3 here. Okay, so those cancel, and they are exactly the same. All right. Any questions about this technique yet? All right, you have 2 problems on the back. I'd like you to try them both. See if you can do these. Okay. Okay, that was good. Well, this is e to the minus y, so if we bring it over here, it's e to the y plus y. Okay. Plus y. Yeah, when you divide by e to the minus y, you get e to the plus y. So this is just e to the y. So there's no minuses. So the minus goes away. Right, so plug it back in and see if it works. Okay. For number 3, just put this up here. This looks very familiar, doesn't it? Let's move the 2 over here. That's the problem we did just a minute ago. Someone have a candidate solution? Someone have a candidate solution? Possible solution? We can test. No one? Yes.
I'm not sure this is right, but I did it the same way we did for example, and I got AE x to the squared divided by 2.
I'm sorry, a little slower. A e to the
X squared over 2, and then divided by 2.
this whole thing divided by 2, like that.
Yeah.
Okay, let's try. Let's see what we get. So y prime equals a e x squared over 2 times derivative of x squared over 2 is just x, right? We want to see if that's equal to y squared, a e x squared over 2 squared times x. I already see a likely problem in that this is going to have an a squared in it. Didn't look okay. You see, it's real easy to check, right? It might be hard to figure out. But okay. Thank you. Someone else have a candidate solution? I'm hearing a. Come on up. Just write it on the board. Come on. Nobody will bite you. I'll let you go after you write it. How about that? Okay. Oh, just -2 over x squared. Okay. Y equals -2 over x squared. Okay, let's give this a try. So y prime. Oh. So y prime equals, so this is x to the -2, so -2 times -2, right? And then we're just left with an x, so 4 over x. So the question is x times -2 over x squared squared. 4, that worked out good. X cubed. Did I do something wrong? Or do you have another?
I think y prime is 4 over x cubed.
I'm sorry?
I don't think you took the derivative right.
Oh, I did take the derivative right. Okay, let me try again. So if this is -2x to the -2, oh, so it should be 4x to the -3. Very good. Yes?
So what we do is we don't have to have the plus c at the end.
Sorry?
We don't need the plus c like at the end.
Well, I asked for a solution. Yeah, that's me. Don't worry about it. there probably should be some undefined constant in here. Let's go find it. So dy 1 over y squared equals x dx. So this should be negative 1 over y equals x squared over 2 plus a constant. Or y equals negative 1 over x squared over 2 plus c. Or negative 2 over x squared plus c. So if we put the constant there, I think we're okay. All right? I'll let you verify that. Okay. How about number 4? Have a solution. Let's write number 4 down. dy dx. You know, I forgot to say something at the beginning about differential equations. They can be hard, right? This is kind of tricky. We're going to see something on Tuesday where some differential equations are actually quite easy. If you remember your high school algebra. But, okay, x e to the negative x, is that it? No, e to the negative y. Okay, that's very different. Okay, does anyone have a candidate solution for this? I know you do.
Natural log of x cubed, x squared over 2.
Natural log of
X squared over 2. No, inside or inside over 2. Plus
that's the end? Okay, let's check it out. So y prime equals 1 over x squared over 2. Puts the 2 up here. And that's supposed to equal x times e to the log of x squared over 2, which is x times x squared over... that didn't work, did it? Did I do something wrong? Oh, you know what? I already did this wrong. Found the derivative... let me try this again. 1 over x squared over 2 times the derivative of x squared, I forgot that, 2x, right? So that's 4 over x. But that didn't turn out right. Did I do something wrong?
That's a negative 1. I'm sorry.
Oh! Well, that makes a lot of difference, doesn't it? Okay, so it's x over e to the log of x squared over 2, which is x over x squared over 2. I'm getting closer. So I ended up with 2 over x.
Yeah, but on the derivative of the natural log, you don't have to put the 2 on it.
Let's try. Derivative is 1 over x squared over 2 times 2x, right?
Over 2. You have a 2.
Oh, yes. Thank you. Okay. Correct. All right. Okay, we're gonna look at one more thing today. We've talked about differential equations in general. We solved a few simple ones. We now have a powerful technique to solve some of these equations. But some of these are going to be very difficult to solve. Maybe we can't do them in closed form this way. And so I'm going to show you a tool we have to kind of get a feel for what the solution might look like. So this is going to take some very careful artwork on my part. One, two, four. Now I'm going to do this on the board, which is a little tedious. I just want you to imagine for a second, in today's modern world, you would have something to do this for you, right? It would be like a computer program. So, I don't know how much of this I'll need. So here's the differential equation I want to try and get the scope of. Y prime equals x plus y. And I'm interested in the initial condition y0 equals 1. So what we're going to do here is we're going to draw something called a direction field. This is a diagram to try and help you get a feel for what all these solutions might look like. Right? So we do this, again, it's a little tedious, but let's start off at the origin. X plus y is 0, so the derivative is 0. So I know that very close to this point, I'm just going to draw a little bar here. Right? Now, let's come out here to 1, 0 and say, all right, what's the derivative at 1, 0? Well, x plus y is 1, so the slope here is 1. Oh, okay. So the slope here was a half. Slope here a little more. Here it's 2. Here it's 3. These are approximate, and here it's 4. Okay. We could kind of do the same thing up here. Here it's a half. Here it's 1. 1.5. 2. Okay. A half plus a half. Here it's 1. Here again it's 2. There's a certain symmetry you can kind of see growing here. Right? 1, 2, 1.5, 3. Okay. So as I move up either in this direction or that direction, the slopes go from 0, and they kind of move further and further up. Right? Let's move backwards a little here. So at -1 here, now it's -1. And it's going to get steeper and steeper as I move out. It's not so steep here. This point 1, -1, it's 0 again. In fact, here it's 0. So the slopes along the diagonal here are all 0. Okay? I know this is a little boring. We're not going to do it very much. But the result is worthwhile. It really is. Okay, so again, as I move up this way, the slopes increase. And as I move this way, they decrease. So both those things are kind of happening. All right, let's go down here a little. This is -1, right? -0.5, -2. And again, over here, I get this kind of mixed kind of thing. Along the diagonal, it's always 0, because x plus y is always 0 along the diagonal. But again, as I move this way, they start to move up. And if I go down, they start to move down. All right? So we just have this quadrant to think about. Now here, everything just gets more negative more quickly. I'm just going to paint in a few because my artistic ability is waning quickly here. I don't know if you've noticed. Okay, so we kind of have a rough idea what's going on here, but let's try and take a look here. So if I start out at some point here, it seems like it kind of goes that way. And again, here, these are kind of going up this way. Remember, this is a family of solutions, so each of these lines represents a solution. And then here, kind of goes straight down. Again, here there's some critical point here where we start going up again. And then finally over here, they start going off in this direction. It's kind of, if you think of like a river, like the flow coming in, right? So if you're in one spot, you kind of, you have to follow one of these tributaries, right? But overall, just kind of a flow. Okay, so I asked the question, what happens at y0? If that's equal to 1. So let's find out. So if 0 equals what does that mean? That means along the y-axis it's 1. So this is actually this particular solution that we're looking for, right? Just one of the possible solutions. Okay. Now, you might want to ask, okay, it's a pretty picture, but it doesn't really help us that much, does it? I mean, we can get a feel for what's going on, but we can see that, depending upon where we are, the solution to this differential equation, the function might look very different. It might kind of curve up. It might kind of go straight through. It might kind of curve down. But what if we really wanted some real data? We wanted some real data points. So how would we go about doing that? And one way we could do that is we could start at some point here. Let's say, so and then y dx. So 1. So what if we were to just start here and then just go a little way in this direction, some little dx, right? So for a very, very small x here, we could approximate this curve by a straight line. So what I'm saying is, if we want to move dx along here, right, we know that the derivative is 1. So for a very small distance, this would just be 1 plus that small delta x. Well, okay, then we can calculate the dy dx here. It's x plus y, so it's 1 plus delta x is 1 plus 2 delta x. Right? So we could now repeat this. Say another delta x here. This would be 2 delta x. And again, now the computation gets a little more complicated. Right? Because now we're starting at 1 plus delta x, and now the derivative dy dx is a little more complicated, but we're going to add, what, 2 delta, well no, we're just going 1 delta, right? So it's just going to be 2 delta x squared plus delta x, right? Another delta x. Okay, you can see it gets a little complicated here. But that's only if you want to do it algebraically. What's the obvious solution, practical solution to figuring this out? You get a computer, right? You write a computer program that says, okay, this is where we want to start, and then just pop out the data. I'm going to try one more time here. See if I can get the cam to work. If it doesn't work, I'm going to have to go like this. Working. Anybody see any action up there at the projector? Oh, goodness gracious. Okay. So, I think I've said this at least a couple times. This is not a computer programming class, so some of you will appreciate this and some of you will appreciate it less, but that's okay. This will further in. Okay. So this is code. You don't really have to understand too much about it. This is written in the C language, so you can tell because at the very top it's the C language, or C++, it'll say main. And then down here, this is not a graphics program that you just execute it from a command line. And I print out a little message saying what I'm going to do. But let's just jump right in here and try and see what's going to happen. So this line up here says for. All you really need to know is we're going to loop inside of this statement, right? Because what are we going to do here? We're going to loop, right? And the first thing I do, a little above here, I must have initialized x1 and y1, and I calculate the slope, right? And there's a pretty common usage of slope, right? So whatever x values I have for x1 and y1, now m has my slope. And now I want to calculate my next x2. So I just add some small value I call dx to x1, and that gives me my x2. Is this going to autofocus okay? And then finally down here, well, try and think of in your head, y equals mx plus b, right? So here I am calculating the b value. And once I calculate the b value, I can now calculate the new y value. This is where my mx plus b comes in. And now below you see a little note. I reset my variables. I move my x2 to my x1, my y2 to my y1, and I go back in the loop. And somewhere along here I probably print out some values. So I just want to show you, this is some output from this program. What I've done here is I've plugged in different little values for the dx. So here I plug in 0.1, and you can see I run down 0 to 1, that's the first point, 0.1, 1.1, and then I move along down through these values. If I then run the program again, but with a still smaller value, well, it's going to take me 10 times as many loops to get through the same list, right? So I just don't print them all. But you can see here that the values on the left and the right are similar, but they're not identical. Again, if I push this up to 0.001, again, close. And then finally, if you compare this value with now, I'm using 1,000th, you can see I'm almost getting the same value now. In other words, if I use a smaller and smaller value, I'll converge on a particular line going through here. Okay, well, I didn't expect really to get quite this far, but there's some homework doing some solving some separable differential equations for Tuesday, along with the homework for the improper integration. And then on Tuesday, we're going to do a little more. We're going to take a different approach to differential equations. We're going to solve a different family of equations, and we'll go from there. Okay, thank you. Good. I'm just putting something in my box. Solve a differential equation. The variable here is what we're saying is the derivative of y is x times y squared. Right, separate
Niente lo so.
Let's do it. It's the same process.
They're getting that.
Separate variables.